Hello, hi everyone. Can you hear me?
Yes.
Okay, great. Okay, so let's wait probably 1 or 2 minutes before we get started. This has been a really busy week. Okay, so great to see many of you. It's an exciting time. We'll dive a little bit into the AI development today because there's so many exciting things. Um, just before our meeting, I was searching online to find some interesting articles, and so we can share and some interesting news as well. Okay, so maybe probably 1 more minute before we get started. And I also do want to take the time to talk about our new website that Yi and I built. And it's a great place where we can find a lot of centralized information about AI, in amazing things that we are doing in our group. Okay, let's see. I think no 3 minutes. Okay, so let's get started. Okay. So great to see everyone, and I'm excited to talk about the RAG. I can't really wait to talk about RAG, the retrieval augmented generation, because this has been a buzzword and really, sweep the really sweep a lot of areas. So it is the newest development in AI, which ground the large language models, the language models behavior. So we can do data extraction, we can do similarity search, etc. We will dive into that. But before that, let me share my screen so be able to see some of the exciting things. First, we built this website. I'll share the website address so you'll be able to access. Is alive now. Let me share that through my chat. Can you all see my browser? Is my browser
Yes.
shared? Okay, great.
Yes.
Okay. So this is the new website that we built is at usto.edu. It's we built this using WordPress. So in case you want to learn WordPress, I would highly recommend you to do that. So actually, this is the second time I built a website, and I did that in using probably maybe a few days, and of course, with great help from Yi. But it's fairly straightforward if you use WordPress. Okay, much easier than writing your own HTML, CSS, and JavaScript. Okay, so what we would have here in this website is that we put a lot of information here. For example, many of you are familiar with the certificate program we offer both at WashU and also for working professionals. So this give you a lot of information about the AI BDA program that I built for the Brown School, which are offered to all WashU students. And this advanced learning certificate is for working professionals. We have offered this for 2 consecutive years, and we have trained more than 110 students worldwide. And this is what I want to draw your attention, the workshop series. If you click this, you will see that we are going to have new talks coming. So this AI workshop series was commissioned by the Provost Office. And the aim of the workshop series is to introduce AI technology to faculty and students across the campus, regardless of the school you are in and whether you are a faculty or a graduate student or undergraduate student, you can benefit from participating in this AI workshop series. And the name of the series is called Unlock the Potential of AI in Higher Education. And Yu and I are preparing for the very first talk in the series is called How to Build Your Own AI Tutor with GPTs workshop. So if you are interested in building your own AI tutor that can answer any questions you have regarding any textbook or any lecture notes, available to you 24/7, and give you quizzes, summarize concept for you, explain difficult problems, and give you hands-on exercise, then I would say this workshop really works for you. So if you have time and interest, I would highly encourage you to fill in this workshop registration form, so that we'll send you the link and then you can participate. The date is going to be on February 27th. It's a Tuesday, from 12 to 1 p.m. It's a webinar through Zoom, so whenever no matter where you stay, you can participate. Okay. And we are going to offer bi-weekly workshops. This is the first one in the series, and every 2 weeks we're going to offer a new one. Okay, so stay tuned for more information, more upcoming webinars. Okay, and what else? Our AI interest group is online. So if you click here, you will be led to the AI interest group. And as all of you take part in this AI interest group and active contribute to that, we are glad to share with you that all the contents have been online. So if you click here, you will be led to the YouTube video recordings, so you have access to all the previously offered workshops. So there probably we missed only one because we forgot to record that workshop, but all the other workshops are available there. And if you offer workshop, you will see your portrait and your name shown here. Okay, so we do acknowledge your individual efforts. Okay. And also, you'll be able to see all our members. So let us know if we miss anyone. Okay, because previously you sent you a survey. So all of you who have participated in the survey should have your name here. And this is going to be a growing list and evolving list. Also, let us know, right? If you do not want to participate in AI interest group, of course, it's completely voluntary. There's no strings at all, except for your interest, right? So if you don't want your name to be shown here, or if you don't want to participate, also let us know. Okay, that is completely fine with us. Now we have about I don't exactly. You do know the number? How many members do we have now? Active members?
Around 33.
Around 33. Okay, great. So that is a good number. Okay, so our member is going to grow. Okay, and what else? The open classroom talks. All the open classroom talks on the AI series are here. So in case you want to take a look of the previous recordings, we had quite a lot. Okay, so feel free to take part in this if you're interested. And also, our group are active in developing AI applications. So we are going to show more about the application development, the applications we are actively working on here. So we'll keep you updated here. And AI policies. Several of us are involved in summarizing university AI policies across top-tier universities in the U.S. And the goal of that is to write a white paper to inform the campus, the provost office, when WashU try to develop and refine its own policy, they can lean on our white paper report. And finally, scientific publications, we listed all the scientific publication is growing. So just by the time that we publish this, we have 2 new papers that we haven't really added to the list. Okay, so later on, when you think about developing your your papers and you want to collaborate, let us know, and we are more than happy to be part of the effort. Okay. So that's a lot of information. So feel free to browse this website. It's really for us in case you're interested. Okay, so that's for the website. And what else? A few interesting, actually many interesting things happened. We pick up a few to just briefly talk about. So here, let's see. So I don't know how many of you really pay much attention to the Apple Vision Pro. Do I don't know whether can you see this? Oh, screen sharing is paused. Okay, so I have to stop share and share. Probably I'll share my desktop so you'll be able to see everything. Okay, one is the Apple Vision Pro. Apple Vision Pro has been out the market, and all the products have been purchased within the first few minutes when it was on the market. But then there were a lot of complaint over the internet regarding the Vision Pro, although, well, it is first of its kind, it's got spatial computation and definitely more advanced compared to the Quest and other smart glasses. But the main problem is it's too heavy. So basically you wear an entire computer on your head and very quickly you feel tired, you feel dizzy. And you feel isolated. So no, because people can barely see you and you can barely see people, you are very much embedded into this virtual world, which could be lonely. Okay, so if you, I don't know, any of you have purchased the Vision Pro, and it's not cheap. It's almost $4,000. Okay, if you add the tax, so it's quite expensive. And I haven't got one, so probably I need additional funding to purchase one. But I am not a big fan of this kind of virtual reality headset. No, I think it's just way too heavy and not easy to manipulate. I'll wait for the technology to be more mature. Oh, okay. So Kakata said, I had Vision Pro demo a few days ago. Pretty mind-blowing. That's great. That's great. It's great to hear, right? So I heard a lot of good things as well. It's definitely the first of its kind, right? It's very immersive. And I hear that the quality of the visual and audio are excellent. And yeah, it's just a cool stuff to have, but it's not something that you can wear all day. Okay, great. Yeah, even the battery backup is not great. The battery. I think the problem is that they intentionally use the wear and you can put your battery on your pocket. But the problem is that you feel heavier on your forehead because now the weight is very much unbalanced towards your forehead. Okay. Because you don't have a battery at your back head. Okay. So okay, great. So that is another interesting thing. The Humans AI pen. Now everyone think about how they are going to replace the Apple, the iPhone, right? iPhone has been in the market for 15 years, and it's time to think about the next iPhone, right? Something that can replace iPhone. It's a grand idea, because somehow, Steve Jobs, the vision is still very much haunting, in the AI world. And everyone want to think about how they are going to break this spell by inventing something that can replace iPhone. Okay, the Humans AI pen is one of those many efforts. And indeed, the developer were originally from Apple. And they developed this pen as an alternative. So this pen will be able to talk to you, will be able to project the text if you need, and listen constantly to your conversation and do the translation, etc. Right? But it's screenless. It doesn't have a screen. And it's not cheap, right? You have to pay $700 to get this pin, and about $30 per month to get their services. Okay. Will you really use it to replace iPhone, to replace your phone? Unlikely, right? Because no matter how people criticize the screen, we very much need a screen. So I think that's the problem, right? We don't know how far it's going to go. I think it definitely had an advantage. But would you have a pin, 24/7 on your shirt? I'm not sure. Okay. But that's an interesting idea. Okay. Another interesting idea is this cute rabbit. It's called Rabbit R1, and it's very cheap. Of course, in comparison to iPhone or human AI pin, is $200. Okay, and the idea of this rabbit is that they embed the so-called large action model, not the large language model, it's the large action model, LLM or LLM model, to integrate with all the APIs, okay, all the apps, for example. So we know large language models a lot, right? But large action model means that this model will be able to understand all the APIs, all your apps on your phone. So the LLM model can manipulate those apps with no supervision. Okay, so you just need to talk to Rabbit to use all for example, the apps on your iPhone or on Android phone. Okay, you only need to set up once, and then you can auto control all those apps by just saying a few words to the rabbit. Okay. So the idea is to put all the apps in the rabbit hole so that you can use language to control them. Okay, very interesting idea, but don't know. Is in pre-order. We don't know how far it's going to go, or how mature the technology is. Okay. Another interesting idea, which really I'm a fan of, is I tend to believe, or at least I'm a fan of smart glasses, because I wear glass every day, and you generally add additional burden if you wear AI glasses versus the traditional glasses. If they are about the same weight, they're about the same same style. Okay, so the most recent the market is there, but none of the smart glasses are so far successful, unfortunately. There's a new invention called I think it's called AI frame or frame AI. Yesterday I could find it, but now I couldn't find it anymore. I don't know where it is. But no, you can definitely check later. Or maybe it's this one. No, it's not this one. But anyway, so it's a new design of the smart glasses that give you augmented reality. It can project what has been taught to the screen, do the real-time translation, and print that on your glasses. It can do a lot of practical stuff that you need when you interact with the AI system, but without losing your connection to the world. Okay. So definitely check that out. I couldn't really find the website for now, but if I find, I'll share it with that with you later. Okay. Okay. So any questions? Any comments? Anything you want to share? Okay, then we'll go to our topic, right? So I told you that I'm going to give a talk on the rack, but I'm a little bit too optimistic. I think I will be able to do this presentation slides, etc. But I haven't got time to do that. But it's okay. We can just talk, right? Really, whether we have presentation slide or not is not important. Really, that we understand, the concept of the rack or the retrieval augmented generation. Okay. So here, as you can see, that I'm using the website, the web pages from the PyCon, and we are going to actually use PyCon quite a bit a little later. Okay. And PyCon is a pioneer company, a startup company focusing purely on vector database. Okay, they built probably one of the largest and most comprehensive vector database to be accessible worldwide. Okay. And to understand RAG, we need to understand vector database. And to understand vector database, we need to understand vector embeddings. Okay, so that's why we need to talk about vector embeddings first. Okay. And of course, you can read the web pages, and I'll share that with you here through the chat. But I'm going to just talk through very quickly, and then we'll dive into implementation. Right. So first, what is vector embedding? So vector embedding basically means that we are going to transform the data, usually unstructured data, for example, text and images, audios, the visuals, into floating numbers. Okay, basically numbers with decimal points. Okay. And why we want to do that? Because we would if we convert those unstructured data into the floating numbers, then we'll be able to manipulate those numbers. We can feed those numbers to the model. We can do similarity search, etc. Okay, so basically, remember, machine understand nothing but numbers. Okay, so if we want machine to do anything, we have to convert them into numbers. Okay. So therefore, for the unstructured data, the way we want to feed them to the model, or the way we want machine to manipulate, is to convert them to numbers. Okay. So, and we are going to use vector embeddings to convert those unstructured data into numbers. A very simple example of vector database is when you have x-axis and y-axis, and we represent dot in this two-dimensional space, right? And how we represent a dot, that is to use coordinate, right? X coordinate, y coordinate. For example, this dot is represented 1, 1, right? So basically 1, 1 give you the coordinates and the basically position of this dot in this two-dimensional space, right? X and y axis. Okay. And that is exactly what the vector embedding is doing. It's going to represent a data point into a vector. And in this vector, we have numbers to represent position of that vector. For example, in this two-dimensional space, we are going to represent this dot with a vector of 1 and 1, right? 2 elements in this vector. But as you can guess, we can have multiple dimensions, right? We can easily extend this to n dimension, so that we are going to have n floating numbers in this vector to represent the position of that data point. Right? Okay. So if we can represent a single data point, of course we can represent many data points, right? For example, here, each dot here has its own x and y coordinate, and then something really interesting happened, because now we can study the relationship between those dots, right? Those data points. For example, the 3 blue light blue dots, they are clustered, and why do we know that? Because the coordinates were very close, right? The distances between those dots were small, right? In this case, we will say there are similarities of those 3 dots here, right? On the other hand, we will see this dot, the black dots, and this dark blue dots, they are in the opposite direction, right? And they are far away from each other. So here we will say that these 2 data points are dissimilar, right? Or you will say they are in the opposite direction, right? So actually from this, just using two-dimensional space, we'll be able to represent the similarities and dissimilarities between multiple points. Okay, so that is an interesting, really interesting phenomenon, right? We can as long as we can convert our data into vectors, and then we can start calculating distances between each pair of those vectors, and the distance will represent how similar or distant the pair of dots are. Okay. And then we can extend this, of course, to n-dimensional space, right? In this n-dimensional space, we can calculate the distances between those dots. And of course, those distances still represent the similarity or the degree of dissimilarity between those dots, between the data points. Okay. And then, well, the first embedding, so that is the idea of embedding. Okay. And the first, probably not the first, but really famous and now classic embedding model is called word-to-vec. Okay. Basically converting English words to vector. Okay. So it's called word-to-vec. Now, believe it or not, when I first learned machine learning, probably 4 or 5 years ago, and I came up with this, I came upon this word-to-vec, and at that time it was the state of the art. Okay, so many models use word-to-vec, but nowadays, if you learn machine learning, you almost never heard of this model, right? This is how fast the AI world is spinning. Okay, so when we talk about AI history, people talk about word-to-vec, but it's not that old actually. Okay. So the word-to-vec model is very simple. So basically, it's mapping each word into a multi-dimensional vector space. Okay, and then you start to calculate the distances between them, and the distances will represent how similar or how different those words are. Okay. Of course, it's in the multi-dimensional space. I don't really recall the dimensionality, but probably a few hundred dimensionalities, maybe 200, 300, etc. Right? They have different dimensions as well. They have different submodels. But well, no, our human vision only probably can see up to 3 dimensions, right? So that's map the multi-dimensional word-to-vec model into and project that into just 2 dimensions, right here, right? So this is much easier to see. And look at those words. Okay, consider we have the universe of all the English words, probably millions of words in this galaxy, and the words representing location are fairly close to each other. If you see here, in the middle, we have the located. And besides, we have near, south, housed, lies, area, centers, location, erected, tongue, opened, renamed, right? So, you don't need to have a lot of imagination to see that those words, to some extent, all represent some location, right? And those words, in the word-to-vec space, even when we project to 2-dimensional, that is a significant loss of information, we can still see that those words are clustered, right? Much closer compared to all the other words. Okay. So this really tells you the key idea of embedding. Okay. So the embedding allow us to compare similarities by calculating distances between any pair of data. Okay, and that is a very powerful idea. Okay. And the way it works now is you have some raw data, right? Doesn't matter, it's text data or image data, and then you apply an embedding model. Okay, there are many embedding models there. Of course, if you don't like them, you can create your own embedding model by creating a neural network. If you have taken my deep learning course, you know how to do that. Okay, but the reality is you don't need to do that, right? Because there are, well, all those large language models that create embeddings that are very effective, right? And you can use that embedding model. You can use the embedding model from from GPT-4, from Llama 2, from Mistral, from Cohere, you name it, right? So basically, you borrow an embedding model, and you put raw data through the embedding model, and then all the words, all the tokens, for example, will be converted into vectors. Okay, so it's as easy as this. Okay, so you can think of this existing embedding model is just a mathematical function that's going to map your raw data on the one hand to the vectors on the other hand. And when you put those vectors together, we are going to have a vector index. Okay. Okay. So what you can do with vector embeddings, you can do semantic search, basically search similarities. You can do question answering applications. You can do image search because fundamentally, no, if the two images are similar to each other, then they are going to be closer, right? As easy as this, right? If two images, their vector representation are farther apart, it means these two images are not similar, right? So and that is actually how you can find you use Google Lens to find the images that are close to each other, right? You can do, of course, do all this kind of search. You can do audio search. You can do recommender system because fundamentally recommender system is about using what you, for example, in movie watching, there's matching what you already watched to some new movies or other movies that look similar to your movie in this multi-dimensional space represented by the vector database. Okay. And anomaly detection. Of course, if you know what is the norm is represented by the vector databases, and then the outliers in the vector database would be the abnormal things, right? That is anomaly, right? The outliers. Right? So that is the vector embedding. Any questions so far? Okay, good. Then feel free to ask questions if you have any. Okay. And then, yes, after we talk about vector embedding, we'll talk about vector database, right? And vector database is nothing more than the assemble of vector embeddings. Okay. And how it works is this. Okay. So you first have some content. It could be images, it could be audios, visuals, text, and you feed those content, basically your data, into this embedding model that we talk about. And then that we also mentioned that the embedding model is just to convert your data into the vector embeddings. Basically, it's just a vector of a certain dimension, and in the vector there are floating point numbers. And then the vector database is just a symbol of all the vector embeddings. Okay, put them together. I mean, you could think of stacking them together, but of course, a little bit complicated than stacking them together because they need to make sure that the vector database is optimized for searching and computation. But basically, it's just an ensemble of the vector embeddings. And then what we could do with this vector database? Well, we can start our application. Okay, so a simple application would be a question, right? You want to ask a question about this vector database. Okay, say you in the application you write a prompt to ask a question, or you provide the image and ask what images in the vector database look similar as the image that provide, right? Or I send an audio file and I ask who this sound is, right? Whose voice this is, right? And then of course for all your query, the images, the text, the prompt, the audios, you send to the embedding model again. And your query will be able to convert it to the vector embedding and convert to a vector as well, right? And then, well, because both your query and the data stored in the vectors are all into this all being converted to those vectors, and then you can do the comparison, right? Basically, you just calculate the distances between your embedded query versus the data in the vector database to see which part of the vector database, which record in the vector database have the lowest distance, right? Closest to the embedding of your query. And then it's going to send that piece of information, this data point from the vector database to you. Okay. Of course, you can do some modifications, right, using large language models to wrap around the information. But basically, it's just a similarity matching process. Okay. Question? Okay. So hopefully the idea is very simple, right? You can definitely read more. And sometimes people use vector database and vector index interchangeably, but there are some differences, in fact. So the vector index is basically a simple stacking of the embeddings. Okay, literally. And there's a famous vector index called FAISS, FAISS. And you can use this vector index locally because this is really good for small to medium problems. You don't need really optimize for the search the efficiency because if you have a small data set, it's going to work really fast. Okay. And sometimes you may need a vector database, which is just an enhanced version of vector index, which is optimized for computation and similarity search. Okay, so it has enhanced capacity to manage your data, manage additional metadata. We'll talk about metadata a little later, and give you additional functionalities such as real-time updates and backup, etc. Right, data security. So basically, you could think of the vector database as an enhanced version or commercialized version of vector index. Okay. So for small problems, I would say a vector index, a free one such as FAISS would be enough. But if you want to build large applications, you are more likely to use a vector database. Okay, and we are going to introduce both in the implementation section. Any questions? Okay, so you can read the rest. It's quite interesting, and hopefully this is easy to understand. And one final thing about the serverless vector database. Hey, so this is a groundbreaking invention. Remember previously, if you, for example, you want to store your data, right, in some places, and then you access the data maybe once a month or once a day, it doesn't really matter. Even on the days that you don't access your data, that you don't do any computation, you are still paying, right? Because there's a fixed cost. Because you are occupying the computation space, even if you are not doing the computation. Okay, so that is commonly done for the vector databases as well. Okay, so previously the vector databases are organized by so-called pods, and you have to purchase the pods to be able to store your data, and then even if you don't use it, it still costs you something. Okay, because you basically purchase those spaces. Okay, for the computation, you have set aside no resources. Even if you don't use it, someone else will not be able to use it. Okay, so you have to pay for that cost. But now we have the serverless vector databases. And the key idea is that they separate the storage from computation. Okay, so previously the storage computation have to happen in the same space. So that even if you do not search, basically doing the computation, you still need to pay, right? But now because of the serverless vector databases that separate the storage from compute, so that if you do not use the vector database, you don't pay for it. Okay, so that dramatically reduces the cost of using vector databases at scale. Okay. And currently, the PyCon offer two options. One is the older part option, but recently they opened up the serverless version. Okay, I just use serverless version. I have a trial, and it works really fast. And good things is you don't pay anything if you don't use it. Okay. So that is the serverless. Now probably we are going to see this roll over to all the places that later on we don't really pay. There's no fixed cost. If you don't use it, no, you don't pay. Okay, so I think that's a great idea, and that is only possible because no, we figure out this how to separate the storage from computation. Okay. Okay, so if you're interested in technical details, you can read the rest, but now let's dive into the implementation. Okay, so any questions? Good. Okay. Okay, so let's take a look of, let's see, here, okay. Let's start with some simple demonstration of the PyCon. Okay, so PyCon is a commercialized vector database, and in the free tier, if you don't want to pay anything, if you don't want to use a credit card, then you can only use the server version. You are given a single part that you can store your only index. You can only create a maximum one index. But you can store large amount of data there. You can store probably 1 million rows, 10 million rows. It doesn't really matter. But no, you only have access to a single. You can only create a single a single database, vector database. Hey, if you delete that database, you can create a new one, but you cannot have simultaneously more than one. Okay. And the version I'm using is the serverless version that you do need to pay, but they give you $100 credit. No, because I'm just experimenting, so I probably have used about 2 cents out of 100. So 100 goes a long way, actually. If you don't extensively use it, it's just for experimenting. You can't really spend $100. I don't think you will be. Okay. Okay, but of course, no, you have to put your credit card there to be able to access the serverless feature. Okay, so here we install the PyCon, and we also have the serverless specification. So this is only possible, only available to you when you have a paid version, and a bunch of other tools that you probably are familiar with. And I'll load my PyCon API key. So you get this API key, even for the free version, you get a PyCon API key. So I saved my key here in the environment. Oh, actually, I'm using the VS Code. It's not the Google Colab that you are familiar with. But you can basically implement this same as in the Google Colab. So later on, I'll share. This is here. This is still an IP1B file. Still a notebook file that you can use in your Colab or your Jupyter notebook. Okay. So here I initialize the PyCon client. Okay. And then I create a serverless index. Okay. So very interestingly, to create this index, you first provide a name. I just call this quick start. You can call it anything you like, and then provide your dimension. So because this is a toy example, so I create a dimension of 8, but usually you want to create a dimension that is the same as your embedding model. Okay. So if you have a particular model in mind, for example, if you want to use GPT-4 model or whatever model, you need to check the dimensionality of that model. Okay, the embedding model is available in the documentation. Okay, read the documentation to get the dimension of that model and put the dimension there. Okay. I forgot on top of my head what is that for the GPT-4. I think it's a few thousand, maybe 3,000 something. Okay. And then the metric basically it tell you how you are going to do a similarity search, right? Because there are various definitions of distance, right? You can have this traditional Euclidean distance, you can have this Manhattan distance, you can have this time dot product, and hopefully everyone knows dot product is just how you multiply two matrices or two arrays. Okay. And here we use dot product as the way to calculate the distance. Right? And then in the serverless specification, you need to provide where you are going to store your data. So I think this is the default. It's going to store in the AWS. Basically, the Amazon provides this cloud, and they have many regions. And I think the default region is US West 2. Okay. Any question?
I have a quick question.
Yeah.
So as to the dimensions, Professor, you mentioned that we need to check the large language models dimension before we set the dimension. So,
Yes.
do we need to set them as the exact same number, or as long as the dimension is smaller than the LLMs?
That's a good question. You have to set exactly the same, right?
Okay.
Exactly the same. It's going to be precise, right? Because otherwise, no, you think about if you calculate distances between two vectors, if the two vectors are not the same size, how you're going to calculate it, right? Because the dot product doesn't exist, right? If you calculate no two vectors of different dimensions. So therefore, the dimensionality must exactly match. So where do we have this? We can find this dimension but it's going to be the GPT for embedding dimension, maybe. Let's see. New embedding models is here, right? Yeah, so this is the dimensionality, right? The small model text embedding 3 small is 1,536, and larger one 374. Yes, it's this one, 3,072. So that is the I think it's GPT-4 dimension. Okay, but you'll be able to find that. Okay. Okay. And then you initiate the index. Okay. Here, no, you initiate this because you just create the index, but you have to initiate the index so that you can start upserting your vectors. Okay. And here we upsert the vector, right? What is upsert? So upsert is basically upload your vectors to this index. Okay. So here you create this vector database or vector index, but this index is empty, right? You haven't put any data there, right? So upsert just means sending my local vectors to be stored in that vector database. Okay. And I provide some vectors. Okay, I provide the ID called vector1, the corresponding values, and look at there, right? So you have to make sure that the vectors is 8-dimensional, right? Because you define the vector as 8-dimensional. Okay, important. Okay, you have to make sure that dimensionality match. Okay. And then this one, namespace. Okay, so think about namespace as a way to make the vector database separate the vector database into smaller sub databases. Okay, and why you want to do that? Because think about how filtering works. Okay. Say, for example, in Amazon, there are probably 100 different categories, right? There are books, there are clothing, and when you do the search, if you just put keyword in the search engine, it will search everything, right? Across all the categories, and it's going to be slower, right? And not very specific, okay? Because you may, if you write, large language model, it may give you a textbook. It may give you, I don't know, something else, right? Maybe a T-shirt, with large language models there, right? So it's not specific. It's a waste of resources if your database is really large, right? We are not talking about thousands or tens of thousands. We are talking about millions or billions of rows. Okay, when you do the search, if you know the namespace of the vectors, you can basically shrink the number of vectors you have to search through, and it's more economical, right? Okay, so meaning that, for example, you are just searching among the books in Amazon. You are not searching the entire database. Okay, so that is the namespace that's allow you to search a sub database. Okay. Okay, yeah. And then so I specify 2 namespaces, and later on, you can search just within the namespace NS1 or NS2. Okay, so this make a difference if you have a very large database. Okay. Okay, and then we can use this describe index static to take a look of the database that we vector database created. We have dimensionality of 8, index phone is 0, namespaces, there's 2 namespaces, and total vector counts. Basically, just give you some statistics about the database you created. And now we can do the query, right? Because we want to know, for example, I want to search in the namespace NS1, and I create a vector. This vector, of course, this is a toy example. I just write a vector of all 0.3s. And of course, this vector has to be the same dimension, right? It has to have 8 dimension, not less, not more, okay? I'm going to search the top 3 matching vectors in the vector database. And let's take a look. So we have this 3 most similar vectors identified. Okay. And give you the ID and a score. Score, basically a higher score means a better matching. And interestingly, the 0.3, this one, we have an exact match, but the score is a little bit lower than this one. There could be some penalizing factor there. So basically, if you have an exact match, it may not be prioritized for some reason. I don't know exactly what you have to really look deeper into the algorithm. But basically, it gives you the 3 most similar, and how they define most similar in the dot product. Basically, they calculate dot product to be able to tell the score, and using score, is of course standardized score. They will give you a ranking of the similarities of the top 3 data points from the vector database that are most similar to the vector that you provide. Okay. Question? Good. Okay. No, you can actually take a look of what's behind the hood in the PyCon console. In the PyCon console, see here, this is the vector database I just created. Okay. You can take a look of the console to know, and this is another one I created. I'll showcase a little later. Okay. Okay. And what else we can do? We can delete an index from here. You can delete, of course, from the console, or you can delete from here. Just use PC delete index. The index going to delete it from the database. If you delete the index, you cannot restore it. Okay, basically it's gone physically. And you can also insert vector with metadata. For example, besides the ID and the value, I have some metadata. I have the JARA comedy, the year 2020. Think about those vectors represent maybe the title of a movie or the description of a movie, right? And then you can provide some metadata, for example, regarding the JARA or the year of the movie. Okay. And why we use metadata? Well, as you can guess, because we can further filter the search results using metadata, right? As a way to be more economical and also be more precise in our search. Okay. So here, if you check the index, we still have 8 dimension, but we have total vector count of 12 because I just added 4 more, right? ID, A, B, C, D, okay, to the vector database. And now I can search not only by the vector, but also by using this filter. See here, in the filter, I wrote, I want the JARA to be documentary. Okay. So this is an equal sign, basically, JARA equals documentary. And I want the year to be 2019. Okay. And I want the top 1 search results. Okay. And then it comes. Hey, so this, if you see the metadata, it matches exactly, right? We have the JARA of documentary, you have year of 2019. Hey, any questions so far? Okay. If you have a lot of data, right? If you have millions and billions of observations, it's going to take quite some time to insert into the database, and you can do that in batches. Okay. So this example basically give you the way that you can upload by batch. So here I just create a function to chunk a large data into batches with a batch size of 100. So every time the model, the vector database, we are going to insert 100 observations, 100 vectors into the vector database. Vector database. Okay. And here is how you implement this. So I observe this. I use this chunk function that chunks function that I created to chunk the data into smaller pieces, and then I'll feed that to the index batch by batch. Okay, so take a closer look later on if you're interested in that. So this only help you if you have a large data set. Okay, for toy examples, for 1,000, even for probably tens of thousands, it may not really boost your productivity that much. But you have really large data set, then it's going to help you tremendously. Okay. Also, when the machine runs really long, the upsorting may encounter some error. Okay. So there are some additional guidelines, in the PyTorch documents that you can read to avoid and to try out those errors and prevent those errors if you have a really large data set to be uploaded. Okay. Okay, so here, after I do this, batch upsorting, now I have 1,012 vectors in the vector database. Okay, and you can also upsort vectors with sparse values. What do I mean by sparse values? Well, the vectors by default, they are dense values, meaning that they are floating points. I think that the default is float 32. Okay, is the single precision in floating numbers. But well, you may have integers, or you may have the half precision as floating numbers, right? So if you have those values, you can put them in the sparse values. Okay, so here, for example, indexes, they are integers, right? And those values 0.5, 0.2, so they are not stored in float 32. Okay, but well, the previously the PyTorch did not support sparse values. You can only have the dense values. But now they added this functionality, which I would say is great. Okay, and now you can search by both the vector value and the sparse values. Here is an example. I'm going to make a query. Here I am going to have this vector, and then I'm going to also have a sparse vector taking the index values and the values here. So if you take a look, I intentionally make this really close. Okay, so the index here, this is 10, 15, 12, and we have two vectors. This vector is closer, right? We have 10, 15, and 16. Okay, so if we do this search, not surprisingly, out of these two vectors, vector 1 is closer. Okay, and we have the best match of ID of vector 1. Okay, question? Okay, so you may wonder, well, no, those examples are interesting, but how I'm going to use this, right? In my daily research. Okay, so that is why I'm going to show you here. Let's see. Let's see. Where is my luncheon? So close here. I'll close here. Let me open. It is here. Oh no, is in the desktop. Where is? Oh, okay, it's not here. It should be here. Luncheon. Okay. Okay, great. And now, since you understand about the vector database and the vector index, we can move on to implement some of them, right? And here we are going to use I would say, a very practical example. You could think multiple ways that you can enhance this pipeline and make it really powerful. Okay, so here is just the bare bone of that. I'm going to implement LangChain. Many of you probably know LangChain. If not, LangChain, let me find that. So LangChain is a open source module, or we'll say an ecosystem that chain operations for the large language models. Okay, so basically is simplify how we can communicate with language model and guide the model to do some tasks through prompt engineering. Okay, so that is a one-sentence summary of LangChain, but it's actually an ecosystem. It's fairly developed about, I don't know, maybe about 2 years ago, but very quickly adopted by the AI community and now spread everywhere. Okay, so it's become one of the default way we interact with large language models. Okay, so here we showcase a simple example of how we can use the ideal vector database in using LangChain to link the vector database with large language models to perform some tasks. So this is going to be a basically that is the idea of RAG. Okay, because RAG really is about how you can embed your data into a vector database and then use your language model to access and moderate your data. Okay. So here you need the OpenAI API key because I'm going to use the GPT-4 model. And this one is optional. This one is called the Travity. It's an application to use language model to search factual information from the internet. Okay, so this one is optional. I'm going to basically just demonstrate the first one, okay, using the OpenAI API key. And we can initiate the large the LM, the large language model, the GPT-4 model using the LangChain. Okay, in LangChain, it's got chat OpenAI. Basically, it's going to grab the OpenAI. I think it's GPT-4 model, or maybe I'm wrong. It's 3.5 by default. And then I'm going to write a query, okay? And this query is, what are the key topics covered in each of the 3 sections of the certificate program? You notice that this query has no base, right? It means that if I just shoot this query to the OpenAI model, it's going to give me some very generic answer, right? Sorry, hold a second. I have a phone coming in. Bear with me a second. I'll grab my phone. Okay, apologize for that. And you notice that if we just have this query, the large language model doesn't know what we are talking about, right? So it's going to give us very generic answer. And if you invoke the LLM using the LangChain, and we are going to find out that indeed it gives you a generic answer, right? the message is the key topic covered in the 3 sections of the certificate program may be varying depending on blah, blah, blah. And it's nonsense, right? Because it doesn't really know what certificate program that we refer to. And in LangChain, you can define a prompt template this way, chat prompt template from messages. No, you could say system, tell the system message as you are instructor for the certificate program at a university in the US, and then you provide your input, and then you can train the prompt and LLM together. Okay, so this is the LangChain specific language. Okay, is prompt and then pipe and then LLM. Basically, you train the prompt, basically you feed the prompt into the language model, and then you start to invoke the chain. Okay, if you invoke the chain, you provide the same query. And of course, nothing interesting happened because still the LM model have no knowledge on what certificate program you are referring to. So it gives you a generic answer. And if you don't want this AI message, you want this you want to parse this message, you can use the function here. This is provided by LangChain to parse your output. And you can link the prompt LLM and the output parser together. So this is going to just give you a string, right? But with the same content. The content still doesn't make sense because, again, the LLM doesn't know which certificate program you are referring to. Okay. But now there's something happened, right? Because we learned about the vector database, and now let's create our vector database. Okay, so basically we serve the data, we create a database containing the certificate information into the vector database, so we can make a query to the vector database using large language model and get the feedback modified by the language model as well. Okay. So let's see how this works, right? I'm going to use the LangChain function called the web-based loader. This is really neat because it allows me to just put a URL, and this URL, if you take a look, is our very own certificate program. Okay, information. Okay, so this is certificate program information here. Okay, on a web page, I just need to provide a URL, and then I load the data. Okay. When I load the data, you can take a look at the data. The data is basically just a so-called document. So this is the LangChain specific data type, but it's nothing more than just the text, right, of the web page. Okay, so you can take a look at the web content here. And then I'm going to initiate the OpenAI embeddings, right? Remember, the OpenAI embedding, we are going to use the GPT-4 embeddings with 3072 dimensions. Okay, I'm going to initiate the embedding model, again, using LangChain. And then I'm going to use the LangChain so-called recursive character text splitter to split the text. Okay, the reason why we need to split the text is because this is very extensive, right? If you take a look of the web page, you will see there are, I don't know, maybe a few thousand words, right? Maybe even more, right? So this is quite extensive. And if we want to build a vector database, we want each vector to be relatively smaller. Because in this case, we can do the search much faster, right? So we want to chunk a very large text into smaller pieces. And we are going to do that using the text splitter. Okay. So the text splitter, I don't know what is the default, maybe 1,000 words, maybe something I forgot exactly, but we can probably later on see that. So we are going to chunk them into smaller sizes. And after that, we are going to use the face. Remember, face is the vector index we talk about, right? We are going to use the face to do the embedding. Okay, so it's going to call for the documents which are just the smaller chunks of text, and we are going to use the OpenAI GPT-4 model embeddings. Okay, and in this case, well, we have created a vector, right? A vector index or vector database. Okay, great. And now I'm going to create a new prompt. Okay, and this new prompt is going to serve as the template. Okay. the new prompt looks like this. Answer the following question based on the provided context. Now I'm going to later on insert the context, and the context will be just the vector we created, right? And the question is going to be the query we are going to ask about this context, right? And then we create a document chain using the create staff document chain command in LangChain, okay, by linking the LLM with the prompt template that we wrote. Okay. And after that, there's one more step we need to accomplish before we can build this RAG pipeline, which is called the retriever. Okay. And why we need this retriever? Because when we get this from when we retrieve the data from this vector database, we need this retriever to grab the data from the vector database and feedback into our part of the response. Okay, and later on, actually, we are going to also revise the response using large language models. Okay. So the retriever basically is a way so that after we do the searching process in the vector database, we'll be able to grab the most relevant information from the vector database. Okay, so we'll create this retriever, and then we create the retriever chain. The retriever chain basically just we initiate that retriever and together linked with the document chain that we created previously. Okay. Okay. So if when that is done, we can invoke the retrieval chain. Okay. And by providing the same query. Remember, the query was about what we ask is about what are the key topics covered in each of the 3 sections of the certificate program, right? But now, because we have built a vector database and retrieve information from the database, now the large language model response is grounded by the vector database, right? So therefore, when we retrieve it, and we print the response is a lot better, right? The key topics covered in each of the 3 sections of the certificate program and the follows. Week 1 and 2, overview of the artificial intelligence, AI and machine learning. Week 3 and 6, 3 to 7, week 8 to 15, right? So those are exactly what was mentioned in the web page, right? Okay, so that's hopefully give you a lot of food for thoughts, right? So this is just a bare bone, but it opens tons of application opportunities, right? I don't want to talk more extensively about this. I would say it is your imagination, right? You should think about, well, okay, so now I have this wonderful technology, this RAG system that we built, how we are going to use it, okay? There are just so many potential ways. Okay. Question? Okay. And then I'll showcase how you are going to link your language model with the serverless vector database that we created using PyTorch. Okay. So let me see, open, let me close this. And let's go to RAG. Again, it's going to be here, RAG, PyCon. Okay. Okay. So what we are going to do is I'm going to write some code to upload an entire textbook. Okay. But well, remember, when you upload a textbook, make sure that it's open source, okay? Because there's copyright issues, right? You don't want to upload someone else's textbook that is proprietary, right? Okay, and then be able to ask questions about this textbook. Okay, all through the interaction between large language model, the OpenAI model, and the PyCon database. Okay, so that's how we can do this. We first load the entire PDF textbook. I use the PyPDF loader, and that is provided by Lanchen as well. Okay, so the book is basically here. Okay, if you take a look at this book, we can take a look. Make sure this is a real book. So this is an open source book. If you click here, it's just a PDF book, right? It's very extensive. I don't know how many pages there. 300, about 400 pages. Okay, so this is a large data science textbook, and we are going to embed it. Okay, so here we load this textbook, this PDF textbooks using the PDF loader, and then we can take a look of the loaded file. So this is we print the loaded file. And I also want to know how many documents are in the data, how many pages, show me the page content, etc. So I have 403 documents. Why is that? Because by default, the PDF data loader is going to separate by page. Okay, so because the book has 403 pages, it chunked into 403 documents. Okay, and remember, chunking is important, right? Because we want each vector to be small in size. Okay, and there are how many characters in the sample document? In that document, the page 4, we have 1,797 characters. Okay, and so here is a sample. Okay, page is basically the index page. Okay. Okay, and then again, we are going to chunk the data into the documents into even smaller sizes. We are going to use the chunk size of 500, and we are going to allow 50 as the overlapping. Okay, overlapping means that basically we are going to use the last 50 tokens from the previous page and put into from the previous document put into next chunk. In this case, if we have answers that lie between 2 pages, we'll be able to incorporate that. Okay, so we are going to use the recursive character text splitter to do that. We are going to split the document into a chunk size of 500 characters, okay, with an overlap of 50 characters. Okay. And if you take a look at the small chunks, and you can count that we have now 1,250 documents. Okay, and each document is about 500 characters. It's very, very short. Okay. Okay. Any questions so far? Okay. And now I'm going to fetch my PyCon API key. Okay. So if you want to use the serverless version, remember you have to put your credit card, but you get $100 credit for that. Okay. So, but you do need to have your PyCon API key ready before you can implement this. Okay. So I'm going to fetch my OpenAI key, fetch my PyCon key. I save the both in the environment, and then I can initiate OpenAI embeddings. Okay. This you've already seen this, right? Because I'm going to use the OpenAI GPT model embeddings, and also I'm going to initiate the PyCon. And here you can take a look of the indexes if we've already created. So this was actually we've already created the index. But if you haven't created, you can create from here, and you've already seen the implementation, right? I would say, well, if this is not created in the indexes, then create this index. We provide the index name. So in this case, so this one, this probably is an older model, so it's not 372. 72 is 1,526, 36. Okay, so this is the older OpenAI embedding dimensions. You provide a matrix, basically how you calculate your distances. I'm going to use cosine similarity. Still the same setting for the serverless. And then I initialize the index after we create this index. You can see that the index is already here. Where is my, oh, I closed that. But you should be able to, if I log in, you should be able to see my vector database. It's called data science textbook. Okay. And then I'm going to insert the text into the index. I'll use the Python from text. This is one of the many ways you can insert large amount of text. Here I'm going to insert page by page into the embeddings. And then after that, I initialize the LLM model. And then I also initiate the QA chain. There are many chains you can create in using LangChain, and I'm going to use this QA chain. Actually, this is not necessary. You can create your own chain as well. You won't have to use an existing chain. But this is neat, right? So this is very easy. Just load the QA chain because this is very much standardized. And there are many options for the chain type. I'm going to use the staff. Staff basically is going to give you a detailed answer. There are other options as well. And to make a query, I'll ask, what is adaptive boosting? Okay, so this is a very technical question. But remember here, I'm not querying the LLM, I'm querying the database. Okay, basically the textbook that we inserted. And we are going to run a similarity search, okay, using similarity search. And then I'm going to print the results. By default, it's going to give you the most relevant result. Well, it's a little harder to see because it's really long, but you can actually run the entire QA chain. It's easier to see this way. So this is all the entire response. It include the response. It also include where the response came from. Basically, give you all the sources, all the original documents that were used to generate the response. Okay. But if you just want to take a look of the response itself, you can just call the output text, which just include the generated response. Basically, that is the revised, summarized version of the relevant documents from the vector database. Okay, and the answer is very accurate. Adaptive boosting, also known as AdBoost, is a machine learning algorithm used for binary classification problem, blah, blah, blah. And this is a great answer because this answer is grounded based on the textbook that we provided to the vector database. Okay. Again, hopefully you start to think about the vast applications you can build upon this, right? How powerful this is, and what are your unique applications of this. I would say, yeah, the opportunities are the possibilities are endless. Okay. Any question?
Yeah, I have a question. Is this similarity function a function of LangChain?
Oh, this one.
Yeah, similarity search. Yes.
Similarity search. That is actually, I think it's LangChain. Let's see. It's not. Yeah, I think I'm pretty sure this is a LangChain function. Yeah. So the similarity search basically, I think what it's doing is called the whatever the metric that we applied, for example, here, the cosine, actually, in calculating the distance in the vector database, we specified that we have to use the cosine similarity. Okay, so the search similarity basically just apply that cosine similarity score in calculating the distances between your query and each of the documents in the vector database.
Okay,
Great.
thank you.
Yeah, sure. Any other question?
I have a question, Professor.
Uh-huh.
You mentioned the vector indices and the vector database.
Mm-hmm.
And this one is based on which?
So this one is based on the vector database because we use the commercial version of PyTorch for the implementation, right? Because we insert everything into the PyTorch, so it's a vector database. The previous implementation using the FAISS, so that is a local vector index. It's not a vector database. So when you have a small number of data, I would say use FAISS, okay, because it's free and it's run on your local machine and is pretty fast. But if you have really large data set, right? When I talk about large data set, it's not a single textbook. It's probably tens of thousands of textbooks. Okay, so in this case, you just cannot use FAISS. FAISS is going to collapse. It doesn't have the capacity, and it's not optimized for large data set. In that case, I would say, yeah, you use PyTorch. And of course, there's a cost of using PyTorch. But then you can use all the techniques that we talk about, right? Using namespaces, using meta data, using sparse vector to reduce the search burden and the cost.
Thank you so much.
Great. Yeah, sure. Any other question? Okay, so hopefully, we all learned something from this session. And I'm personally really excited about this wrap, right? And we showcase this in 3 examples from the very basic, the vector database, all the way to implementation, using LangChain, using large language models, using OpenAI embeddings, right? So hopefully, although these are, I would say, toy examples, they really show you the vast potential of applications. Okay, so any final thoughts, questions before we end today's meeting? Okay, so great to see all of you, and we will see you in 2 weeks. Bye, everyone.